Everyone, today we're continuing our veterinary biostatistics series with Talk E, which focuses on three closely related topics: mixed models, Poisson regression, and the analysis of clustered data. These are the tools you need when your data has hierarchical structure, and in veterinary research, that's nearly always the case. Up to this point in the series, we've covered t-tests, ANOVA, linear regression, and logistic regression. Every one of those methods assumes that each observation in your dataset is independent of every other observation. That assumption is convenient mathematically, but it rarely holds in practice. Cows are nested within herds. Patients are nested within clinics. Repeated measurements come from the same animal over time. Litters share a dam and uterine environment. When we ignore that structure and pretend every data point is independent, we get standard errors that are too small, p-values that are too optimistic, and conclusions that don't replicate. This is pseudoreplication, and it's one of the most common statistical errors in veterinary research. Mixed models solve this problem directly. They separate your scientific question, the fixed effects, like treatment, group, or time point, from the data structure, the random effects, like herd or animal ID. By modeling the clustering explicitly, mixed models produce honest standard errors and valid inference. We'll walk through exactly how to set them up, how to read their output, and how to report the intra-class correlation coefficient, or ICC, which quantifies how much of the variation in your outcome is attributable to the clustering variable. We'll then turn to Poisson regression, which handles count and rate outcomes, things like mastitis events per cow, lameness episodes per pen, or disease incidence per 100 cow days at risk. Standard regression can predict negative counts, which is biologically impossible. Poisson regression models the log of the event rate and keeps predictions non-negative. We'll cover offsets for unequal follow-up periods and how to detect and handle overdispersion when the data are more variable than the Poisson model expects. Finally, we'll tie everything together with a clinical scenario, a study of mastitis incidence across 3 housing systems that requires both Poisson regression and mixed modeling. This is where the concepts converge and where you'll see why understanding both tools together is essential for analyzing real veterinary data. By the end of this session, you should be able to recognize when standard models are inappropriate due to clustering, choose the correct mixed model structure, interpret Poisson regression output, including incident rate ratios, and navigate the model selection table that maps outcome type and data structure to the appropriate analytical method. Let's get started. Every standard test and model we've covered, t-tests, ANOVA, linear and logistic regression, rests on one assumption. Every observation is independent of every other. In most veterinary data sets, that's false. Cows within the same herd share feed, water, management practices, disease history, and microbiome. They're not 25 independent observations of the treatment effect. They're 25 correlated measurements from one experimental unit. Treating them as independent gives you artificially small standard errors, inflated test statistics, and p-values that are too small. You see significant results that aren't there. This is pseudoreplication, counting correlated units as if they were independent. The ICC quantifies how serious the problem is. An ICC of 0.3 means 30% of the total variation in your outcome is explained simply by knowing which herd the cow is in, before you've even considered treatment. That's substantial. Above 0.05 and the clustering needs to be accounted for. Below 0.05 and standard models are probably acceptable. The solution is a mixed model. It explicitly models the clustering structure as part of the statistical framework, producing honest standard errors and valid inference. Models have 2 types of effects: fixed and random, and understanding the distinction is the conceptual key to the whole approach. Fixed effects are your scientific question, the predictors you want to estimate and report, treatment group, time point, covariates like BCS and parity. Their interpretation is identical to standard regression. The coefficient is the expected change in outcome per unit change in that predictor, holding all others constant. Random effects are your acknowledgement of the data structure. Rather than estimating a separate coefficient for each herd, which would consume 1 degree of freedom per herd and be impractical in large multi-herd studies, the random effect estimates a single parameter, the variance of the herd level distribution. This captures how much herds differ from each other above and beyond what the fixed effects explain. The random intercept model, your default starting point, allows each herd to have its own baseline level of the outcome. Some herds just produce more milk. Some herds just have lower mastitis rates. The random intercept accommodates that natural variation. It still assumes the treatment effect is the same magnitude in every herd. The random slope model allows the treatment effect to vary between herds. Add it only when you have specific biological reason to expect heterogeneous treatment responses, and only when you have enough animals per herd to estimate the slope reliably. Start simple, add complexity only when justified. Read actual mixed model output. 2 sections, fixed effects and random effects. The fixed effects table looks identical to standard regression. Protocol B increases milk yield by 3.1 liters per day compared to Protocol A, significant at p equals 0.001. Protocol C increases yield by 5.8 liters per day. The key phrase in both interpretations, adjusted for herd level clustering. That's what the random effect achieves. The protocol estimates are now adjusted for the fact that some herds were inherently higher or lower producing. The random effects table tells you whether the clustering mattered. Herd level variance is 8.3. Residual variance is 16.1. ICC equals 8.3 divided by 8.3 plus 16.1, which is 0.34. 34% of milk yield variation is explained simply by which herd the cow is in. That's substantial. If we'd ignored herd structure and run standard linear regression, the standard errors for the protocol effects would have been badly underestimated, producing falsely confident, possibly false positive results. Always report model type, random effect structure, and ICC. A reader who sees ICC equals 0.34 immediately understands why a mixed model was necessary and that the clustering was substantial. Poisson regression handles what both linear and logistic regression can't: count and rate outcomes. How many mastitis episodes did this cow have? How many lameness events per pen per month? How many disease events per 100 cow days? These are counts or rates. Linear regression fails because it can predict negative values, which is impossible when your outcome counts events. Logistic regression is for binary outcomes only. A cow who had 3 mastitis events and 1 lactation is very different from a cow who had 0. That's count information, not binary information. The offset is the most important Poisson concept that gets overlooked. If cow A was observed for 305 days and cow B was sold at 180 days and both had 2 mastitis events, their underlying rates are completely different. Without an offset, the model treats both cows identically, just 2 events each. The offset, log of observation time, tells the model each animal's denominator, converting the analysis from predicting counts to predicting rates per unit time. If follow-up periods are unequal, the offset is not optional. Overdispersion is extremely common in real veterinary count data. Mastitis events cluster by herd, by season, by cow history, all creating more variability than Poisson predicts. Check the deviance divided by degrees of freedom. If it exceeds about 1.5 to 2, standard Poisson is underestimating your standard errors. Switch to negative binomial regression, which accommodates excess variability through an additional dispersion parameter. Model selection table is the practical synthesis of this talk and talk D together. 2 dimensions, outcome type, and data structure. Every regression analysis you'll encounter in veterinary research fits somewhere in this table. When outcome is continuous and data is independent, standard linear regression. When continuous but clustered or repeated, mixed linear model. When binary and independent, logistic regression. When binary and clustered, mixed logistic model, also called GLMM. When outcome is a counter rate, start with Poisson, check for overdispersion, and upgrade to negative binomial if needed. For clustered count data, mixed Poisson or negative binomial. The checklist at the bottom is what to run through before opening any statistical software. Outcome type first, data structure second. For counts, check overdispersion third. The core message of this talk: when you ignore clustering in veterinary data, you underestimate standard errors, inflate test statistics, and generate false positives. The mixed model is not optional complexity. It's the correct model for the data structure that characterizes most veterinary research. Use it whenever your data has a hierarchical structure and report the ICC. This scenario applies every key concept from Talk E. Question 1. Why Poisson, not t-test or ANOVA? The outcome is a count of clinical mastitis events, not normally distributed, not binary, cannot go below 0, and right skewed with many cows having 0 events and a few having several. A t-test or ANOVA would assume normally distributed outcomes and could predict negative mastitis counts, which is biologically impossible. Poisson regression is designed for count and rate data and models the log of the event rate, ensuring predictions stay positive. Question 2. Why the offset? Cows were not all observed for the same number of days. Some were sold or died before lactation end. Without an offset, the model would compare raw event counts. A cow with 3 events in 250 days looks identical to a cow with 3 events in 305 days. Including log, days observed, as an offset tells the model each cow's denominator, converting the comparison from event counts to event rates per unit time. This is the only fair comparison when follow-up periods are unequal. Question 3. Plain language IRR interpretation. Cows housed in tie stalls experienced clinical mastitis at 1.51 times the rate of cows in freestall housing, approximately 51% more mastitis events per day, after accounting for differences in how long cows were observed. For the farm manager, for every 100 days a cow spends in tie stall housing, she gets about 0.76 mastitis events, compared to 0.51 events in free stalls, about half an extra mastitis case per cow per year in tie stalls. Question 4. Deviance divided by degrees of freedom equals 2.1. This indicates overdispersion. The variance in mastitis event counts is substantially greater than what the Poisson model predicts. The standard Poisson model assumes variance equals the mean. Here, the variance is about twice the mean. This means the Poisson model is underestimating standard errors, making confidence intervals too narrow and p-values too small, potentially generating false positive findings. The researcher should should refit the model using negative binomial regression, which includes a dispersion parameter to accommodate excess variability. This will produce wider, more honest confidence intervals. Question 5. Clustering of cows within farms. If all 60 cows in each housing system come from the same 3 farms, 20 cows per housing system per farm, then cows within the same farm share management practices, feed quality, milking hygiene, and herd level disease history. They are not independent observations. This clustering must be accounted for by adding a farm level random effect to the Poisson model, creating a mixed Poisson model or mixed negative binomial given overdispersion. Ignoring farm clustering would underestimate standard errors for the housing system effects, potentially inflating significance. The ICC for farm should be calculated and reported to quantify how much variation is attributable to farm level differences.